Forensic Palynology. The body was found in an empty lot on the city's east side. No witnesses. No weapon. No obvious clues. But when investigators examined the suspect's car, they found something, a thin layer of dust on the floor mats. Inside that dust were pollen grains, microscopic particles from plants that bloom in very specific places at very specific times. The suspect claimed he'd never been to that part of town. The pollen said otherwise. It came from a species that only grows in a 3-block radius around where the body was discovered. This is forensic palynology, the science of using pollen and spores to connect people to places. Different plants release pollen at different times and in different regions. That invisible trace carries a geographic fingerprint. The method works because pollen is everywhere and nearly indestructible. A single breath of air can contain thousands of grains. They settle on clothing, shoes, vehicles, embedding themselves in the smallest crevices. Even after a car is cleaned, pollen remains in tire grooves, air vents, carpet fibers. Washing doesn't remove it all. Time doesn't degrade it. Under a microscope, each grain reveals its species, and with that, its origin. A hiker vanishes in a forest spanning hundreds of miles. Pollen on their jacket shows they were near a specific wildflower that only blooms in 2 valleys. The search zone shrinks from impossible to manageable. In homicides, pollen links suspects to burial sites they swore they'd never visited. The power lies in what can't be controlled. A killer might wipe down surfaces, burn clothes, ditch a weapon. But pollen transfers invisibly. It clings without permission. By the time someone realizes its evidence, it's already too late to remove it. The invisible leaves a trail. And once it's found, the denial starts to unravel. Bloodstain pattern analysis. Blood doesn't just stain. It tells a story. The shape of a droplet, the angle of a spatter, the distance between marks. All of it reveals what happened in the moment's violence unfolded. A single smear can show whether a body was dragged. A cast-off pattern can indicate how many times a weapon was swung. This is bloodstain pattern analysis, the practice of reconstructing events by studying how blood behaves when force is applied. It's not guesswork. Blood follows physics. Gravity, velocity, surface tension. These forces dictate how blood lands, spreads, and dries. The patterns they create are consistent, predictable, readable. When blood falls straight down, it creates a round stain with smooth edges. When it's flung from a moving object, the droplet elongates, forming a tail that points in the direction of travel. The angle of that tail reveals speed and trajectory. By measuring individual drops, analysts can calculate the exact position where the blood originated, sometimes down to inches. Different types of violence leave different patterns. A beating produces small, high-velocity spatter. A stabbing creates medium-velocity spatter with larger stains. Cast-off marks from a swung weapon form linear streaks across walls and ceilings. The number of streaks can indicate how many blows were struck. But blood also reveals what didn't happen. A suspect claims self-defense. The patterns show no signs of a struggle, no defensive wounds. The stains are all low to the ground, consistent with someone already down when the shots were fired. Blood doesn't rewrite itself to match a convenient story. The same applies to staged scenes. A body moved after death leaves transfer stains where blood soaked into fabric and pressed against another surface. If the spatter points one direction but the body faces another, the scene was altered. Blood can be wiped away, but not completely. Luminol reveals traces invisible to the naked eye, glowing under UV light even after aggressive cleaning. Scrubbing removes the stain, but it can't erase the geometry of what already happened. The blood remembers what people try to forget. And once the physics is mapped, the only story left is the one that actually occurred. Forensic entomology. 3 days. That's what the detective needed. When did the victim die? The body was found in a basement. No witnesses, no clear timeline. But on the corpse, there were flies. Not just circling, feeding. And inside the wounds, something else, a larvae, writhing in clusters, each at a specific stage of development. Insects don't lie about time. They follow a biological clock that runs whether anyone's watching or not. The moment a body begins to decompose, it becomes a feeding ground. Blowflies arrive within minutes if the body is accessible, sometimes even before death if there are open wounds. They lay eggs. Those eggs hatch into larvae. The larvae grow, molt, pupate, and emerge as adults, each stage taking a predictable amount of time depending on temperature and environment. This is forensic entomology, the science of using insect evidence to determine time of death. It works because decomposition is a process, and insects are the most reliable witnesses to that process. Different species arrive at different stages. Early colonizers come first, feeding on fresh tissue. Later arrivals prefer advanced decay. By identifying which species are present and measuring their development, investigators can reverse engineer a timeline. Temperature matters. Insects develop faster in heat, slower in cold. A larva that would reach a certain stage in 2 days at 70 degrees might take 5 days at 50. Crime scene investigators measure ambient temperature and compare it to known development rates for each species. The math is precise. The insect doesn't care about alibis. A suspect claims the victim was alive on Tuesday. The insects say otherwise. The larvae recovered from the body are third instar. A stage takes at least 4 days to reach under the recorded conditions. That places death on Friday, not Tuesday. The timeline collapses. The story changes. Bodies found in water, buried underground, or sealed in enclosed spaces still attract insects, just different ones. Aquatic species colonize submerged remains. Soil-dwelling beetles arrive at buried corpses. Even in a locked car trunk, certain flies find their way in through the smallest gaps. The insect record continues. Time doesn't stop. The insects keep feeding, molting, developing. And once you know their schedule, you know the victims. Touch DNA. A hand on a doorknob. Fingers on a steering wheel. A brief grip on someone's arm during a struggle. Contact lasts seconds. The DNA stays for days. Every time skin touches a surface, cells transfer. Invisible, microscopic fragments of genetic material left behind without anyone realizing it. You don't need blood, saliva, or hair. You don't need violence. Just contact. This is touch DNA, also called trace DNA, the recovery of genetic material from surfaces that were simply touched. The science works because human skin constantly sheds. Dead cells slough off with every movement, every brush, every grasp. When you touch something, some of those cells stay behind. And inside each cell is a complete genetic profile. The breakthrough came from improving collection techniques. Traditional DNA analysis required visible biological material. But advances in amplification technology made it possible to analyze samples so small they couldn't be seen. A fingerprint smudge. The handle of a weapon. A shirt collar. The inside of gloves. All of it became evidence. A burglar breaks into a home, careful not to leave fingerprints. But they touch a window frame climbing in, grip a drawer handle searching for valuables, brush against a wall moving through the hallway. Skin cells transfer at every point. When investigators swab those surfaces, the DNA comes back with a match. No blood, no prints. Just contact. The same principle applies to violent crimes. A victim fights back, hands grabbing at the attacker. Skin cells transfer both ways. DNA recovered from under the victim's fingernails identifies the assailant. DNA on the attacker's clothing places the victim's hands there. The interaction is documented at the cellular level. But the method has limits. Touch DNA is a mixture. Multiple people touch the same surface. Their genetic material overlaps, making interpretation difficult. Environmental exposure degrades samples. And because touch DNA is so sensitive, contamination is a constant risk. A crime scene investigator's stray contact can introduce foreign DNA. Still, when the sample is clean and the contact was isolated, the evidence is undeniable. The touch happened. The cells transferred. and the genetic record doesn't forget who was there. Luminol. The room looks clean. Freshly wiped floors. No visible stains. But when the lights go off and the chemical is sprayed, the walls light up. Blue-green glows appear in streaks, smears and spatter patterns invisible moments before. The blood was there all along. Scrubbing only hid it from the naked eye. This is luminol, a chemical compound that reacts with iron in hemoglobin, producing a glow visible in darkness. It doesn't matter if the blood was wiped away diluted or soaked into porous materials. If trace amounts remain, luminol finds them. The reaction is simple. Luminol is mixed with hydrogen peroxide and a base, then sprayed onto a surface. When it contacts hemoglobin, a chemical reaction produces light. The glow lasts only seconds, but that's enough. Investigators photograph the patterns as they appear, documenting the blood evidence before it fades. Cleaned crime scenes become readable again. A bathroom floor wiped spotless glows with cast-off patterns from a weapon. A car interior detailed and vacuumed lights up with transfer stains from a body. A suspect's home, scrubbed for hours, reveals smears on the baseboards where blood pooled and seeped into the wood grain. But luminol doesn't discriminate. It reacts with other substances too. Bleach, rust, certain metals, even some plant materials can trigger false positives. That's why luminol is a screening tool, not confirmation. When it glows, investigators know something is there. Follow-up testing determines if it's blood. The sensitivity is both strength and weakness. Luminol can detect blood diluted to 1 part per million, far beyond what the eye can see. But that same sensitivity means contamination from unrelated sources can confuse the results. A positive reaction has to be verified. Still, when used correctly, luminol turns invisible into visible. The person who cleaned the scene thought they erased the evidence. They didn't. They just made it harder to see until the chemical brought it back. The glow doesn't last, but the record does. Forensic odontology. The fire left almost nothing. Dental records identified the body in 2 days. When soft tissue is gone, when fingerprints are burned away, when DNA is too degraded to sequence, teeth remain. They survive heat, trauma, and decomposition longer than almost anything else in the body. And every person's dental structure is unique. This is forensic odontology, the use of dental evidence to identify human remains and analyze bite marks. It works because teeth are individual. Fillings, crowns, gaps, rotations, the shape of roots. All of it creates a pattern specific to one person. Match that pattern to dental records, and you have an ID. The method has solved cases that would otherwise remain unsolved. Victims of fires, explosions, plane crashes, and mass disasters are identified through their teeth when no other identification is possible. Even in advanced decomposition, the jaw structure holds. Dental forensics can identify remains found years after death, skeletonized and unrecognizable by any other means. Bite mark analysis works differently. When someone bites during an assault, they leave an impression. The teeth create a pattern on skin or other materials, and that pattern can be compared to a suspect's dentition. Spacing between teeth, size, alignment. It all factors into the comparison. But bite mark evidence has limits. Skin distorts. It stretches, swells, and changes shape, making precise matching difficult. The science has faced scrutiny, with some experts questioning its reliability. Courts have become more cautious, requiring stronger corroboration before accepting bite mark testimony alone. Still, dental identification remains one of the most reliable forensic tools. Teeth don't lie about who they belong to. They don't change over time the way soft tissue does. And they leave a record that persists long after everything else is gone. When nothing else remains, the teeth speak, and they give the dead back their names. Gait Analysis. The way someone walks is as individual as their fingerprint. Stride length, foot angle, hip sway, arm movement. Each person moves in a pattern so distinct that even a crowd, they can be identified by motion alone. Disguises change appearance. Gait reveals identity. Security footage captures a robbery. The suspect wears a mask, gloves, bulky clothing. No face. No prints. But investigators watch the way the person moves. A slight limp favoring the left leg. An outward foot turn on each step. Shoulders that barely move despite the stride. This is Gait Analysis, the forensic examination of walking patterns to identify individuals. It works because gait is biomechanical. Bone structure, muscle memory, old injuries, habitual posture, all of it shapes how someone moves. You can change clothes, alter your voice, hide your face. But walking is unconscious. The body remembers. Analysts measure specific markers: step length, cadence, knee flexion, ankle rotation. Each metric creates a profile. When surveillance footage from a crime scene is compared to footage of a suspect walking normally, the patterns either match or they don't. The variables are consistent enough to hold up in court. A bomber walks through an airport. Months later, investigators compare the gait to a suspect's normal stride. The hip rotation matches. The foot placement is identical. The person didn't know they were being identified by the way their body moved through space. But gait can change. Injuries heal. People age. Intentional alteration is possible, though difficult to maintain without conscious effort. Still, the baseline pattern remains. And when the footage is clear and the comparison is thorough, the walk tells the story the disguise tried to hide. Toolmark Examination. A crowbar forced open the back door. Pry marks in the wood. Metal scraped against metal. When investigators recover the tool from a suspect's garage, they test it. The edge of the crowbar is pressed into soft lead, creating a new mark. Under magnification, that test mark is compared to the one left at the crime scene. The striations match. Not similar. Identical. Every tool leaves a signature. Manufacturing imperfections, wear patterns, microscopic scratches on the cutting edge. These create unique marks every time the tool is used. A screwdriver, a knife, a pair of pliers. Each one carries a pattern that transfers to the surface it contacts. This is Toolmark Examination, the comparison of marks left by instruments to the tools suspected of creating them. The method is grounded in physics. When metal meets metal, or metal meets wood, friction and pressure create microscopic grooves. Those grooves are reproducible. Use the same tool the same way, and the pattern repeats. Firearms analysis works the same way. A bullet fired from a gun picks up marks from the barrel's rifling. The firing pin strikes the cartridge, leaving an impression. Ejected casings carry marks from the breech face. Each gun leaves a unique set of marks on every round it fires. Match the marks, and you match the weapon to the crime. A suspect owns a gun. Investigators fire a test round. The marks on the test bullet are compared to the one recovered from the victim. The rifling pattern aligns. The striations overlay perfectly. The gun that fired the test round is the gun that fired the fatal shot. But tools wear down. Marks change over time. A blade that was sharpened, a barrel that was cleaned aggressively. The pattern can shift. That's why toolmark analysis requires precision. The comparison has to account for condition, use, and alteration. Still, when the marks match, the connection is direct. The tool was there, it made contact, and the metal left a record that doesn't lie. Latent print development. The surface looks untouched, no visible prints. But when powder is applied, dusted lightly across the glass, the pattern appears. Ridges and whorls, invisible seconds before, now stand out in stark contrast. The fingerprint was always there. It just needed to be revealed. Not all fingerprints are visible. Most aren't. When fingers touch a surface, they leave behind oils, sweat, and skin residue. These prints are latent, hidden until a technique brings them into view. This is latent print development, the process of making invisible fingerprints visible. Different surfaces require different methods. Porous materials like paper absorb the oils, so chemical treatments are used. Non-porous surfaces like glass or metal hold the oils on the surface, so powder or alternate light sources work better. Powder is the most recognizable method. Fine particles adhere to the oils left by the finger. Magnetic powder, fluorescent powder, carbon-based powder. Each type works on different surfaces and under different conditions. Once applied, the excess is brushed away, leaving the print exposed. But powder doesn't work on everything. Textured surfaces, wet surfaces, surfaces that have been cleaned. These require alternate techniques. Cyanoacrylate, commonly known as superglue fuming, reacts with the moisture in latent prints, turning them white and visible. Alternate light sources like UV or laser make certain residues fluoresce, revealing prints that would otherwise remain hidden. A burglar wears gloves through most of the crime but removes them briefly to handle a window latch. That one touch leaves a print. Days later, investigators fume the latch. The print appears, clear enough to identify. One moment of contact. One permanent record. Latent prints don't last forever. Time, weather, and interference degrade them. But when they're fresh and the surface is favorable, the detail is extraordinary. The ridges are unique. The patterns don't repeat. And once developed, the print becomes evidence that ties a person to a place they claimed they'd never been. Forensic anthropology. The remains were scattered across a hillside, bones weathered and bleaked by months of exposure. No soft tissue. No identification. Just skeletal fragments half buried in dirt. But bones talk. They reveal age, sex, ancestry, height. They show old injuries, diseases, trauma. A fractured rib that healed years ago. A skull with features consistent with a specific population group. Leg bones that indicate someone stood just under 6 feet tall. This is forensic anthropology, the analysis of skeletal remains to establish identity and determine cause of death. When decomposition has erased everything else, the bones remain. And they carry information. Age is estimated through bone development and degeneration. In younger individuals, growth plates haven't fully fused. In older individuals, joints show wear, bones thin, sutures in the skull close. The skeleton ages in predictable patterns, allowing anthropologists to narrow down a range. Sex is determined through pelvic structure and skull features. The female pelvis is wider, adapted for childbirth. Male skulls tend to have more pronounced brow ridges and a sharper jaw angle. These differences aren't absolute, but they guide the analysis. Height comes from long bone measurements. Formulas based on population studies allow anthropologists to estimate stature from the length of the femur or tibia. Ancestry is inferred from cranial features, though this is the most cautious determination, requiring careful interpretation. Trauma tells the story of death, a skull fractured by blunt force, ribs broken by a knife, bullet holes in bone, with entry and exit patterns that indicate direction and angle of fire. The bones record violence in ways soft tissue cannot. But bones also have limits. They don't preserve fingerprints or DNA in the same way tissue does, though some DNA can be extracted from marrow. They don't reveal exact time of death, only a rough window based on decomposition stages and environmental factors. Still, when remains are found and identity is unknown, forensic anthropology builds a profile. That profile narrows the search. It turns unidentified remains into a person with a history, a family, and a name. Gunshot residue analysis. A man claims he wasn't holding the gun when it fired. But when investigators swab his hands, the particles tell a different story. Tiny fragments of burned powder, lid, and primer compounds coat his skin. Invisible to the eye but undeniable under analysis. When a gun is fired, the explosion inside the cartridge releases a cloud of microscopic particles. These particles settle on the shooter's hands, face, and clothing. They're called gunshot residue, or GSR, and they don't wash off easily. This is gunshot residue analysis, the detection and identification of particles produced by firearm discharge. The method works because the chemical composition of GSR is distinct. Lead barium and antimony in specific ratios. These elements come from the primer, the component that ignites the gunpowder. When found together on someone's hands, the implication is clear. Investigators collect samples using adhesive stubs, pressing them gently against the skin to lift particles. The stubs are analyzed under a scanning electron microscope, which identifies the elemental composition of each particle. If the characteristic trio of lead barium and antimony appears, GSR is present. The presence of GSR places someone in proximity to a firearm discharge. It doesn't prove they pulled the trigger, but it narrows the possibilities. A suspect claims they were nowhere near the shooting. GSR on their hands suggests otherwise. But GSR has limits. It transfers easily. Shaking hands with someone who fired a gun can deposit particles. Being in a room where a gun was fired can spread residue through the air. And GSR degrades. Washing hands time and normal activity reduce the amount detectable. The window for collection is narrow, usually within a few hours of the shooting. Still, when GSR is found in significant amounts and the context supports it, the evidence is hard to dismiss. The particles don't lie about their origin. They came from a gun, and they ended up on that person. Digital forensic imaging. Deleted doesn't mean gone. A file removed from a hard drive, a photo erased from a phone, a message wiped from a chat app, none of it truly disappears. The data remains, hidden in sectors the operating system no longer references. And with the right tools, it comes back. This is digital forensic imaging, the process of creating an exact copy of a digital device's storage to recover and analyze data. It's not just about retrieving deleted files. It's about preserving everything: active files, hidden files, system logs, metadata, in a way that maintains the integrity of the evidence. The first step is creating a forensic image, a bit-by-bit copy of the entire storage medium. This isn't a simple file transfer. It's a clone that captures every byte, including empty space where deleted data lingers. The original device is then secured, untouched, while investigators work from the image. Once the image is created, forensic software scans for recoverable data. Deleted files leave traces. Even after a file is removed, the space it occupied isn't immediately overwritten. Until new data fills that space, the old data persists. Recovery tools reconstruct it. A suspect deletes incriminating photos from their computer. Days later, investigators image the hard drive. The photos reappear, pulled from unallocated space. The timestamps show when they were created, accessed, and deleted. The metadata reveals the camera model and GPS coordinates if the location was embedded. But digital evidence is fragile. Continued use of a device overwrites recoverable data. Encryption locks files behind passwords that may be unbreakable. And some applications are designed to erase data securely, making recovery impossible. Still, when the imaging is done properly and the data hasn't been overwritten, the digital trail is extraordinary. Browsing history, communication logs, file transfers, search queries, all of it preserved in a format that doesn't age, doesn't degrade, and doesn't forget. The device tells the story its user tried to erase. And once the image is made, that story is permanent. Postmortem interval estimation. How long has the body been dead? That's the question. Minutes, hours, weeks. The timeline changes everything. It shifts alibis, narrows suspect lists, rewrites the investigation. The body cools. Muscles stiffen. Skin discolors. Decomposition follows a sequence, and every stage offers clues. In the first hours, body temperature drops predictably, about 1.5 degrees per hour under average conditions. Rigor mortis sets in within a few hours, peaks, then fades. Livor mortis, the pooling of blood in the lowest parts of the body, settles and fixes. This is postmortem interval estimation, the science of determining how much time has passed since death. It's not a single test. It's a combination of observations, measurements, and environmental factors that together construct a timeline. Early stages are the most reliable. A body found still warm, with no rigor, died recently. A body in full rigor, with fixed lividity, has been dead longer. But temperature, humidity, and exposure alter the rate. A body in a cool basement decomposes slower than one left in summer heat. Insects, animals, water, all of it changes the clock. As time extends, the markers become less precise. Decomposition accelerates. Soft tissue breaks down. Bloating occurs. Eventually, skeletonization begins. At this stage, time of death becomes a range measured in weeks or months, not hours. Forensic entomology helps. Insect colonization follows a predictable pattern, and the developmental stage of larva narrows the window. Chemical analysis of decomposition byproducts offers additional data. But precision fades the longer the interval. A suspect claims the victim was alive on a specific day. The body's condition says otherwise. The rigor, the lividity, the decomposition stage, all of it points to an earlier death. The timeline doesn't match the story. And once the interval is established, the alibi collapses. Diatom testing. A body is pulled from a river. The question isn't just who, but where. Did the victim drown here, or was the body dumped after death elsewhere? Diatoms answer that. These microscopic algae live in water, and every body of water has a distinct population. Lakes, rivers, ponds, even tap water. Each carries a unique mix of species. When someone drowns, they inhale water. Diatoms enter the lungs, and if the heart is still beating, they're carried into the bloodstream, spreading to organs throughout the body. This is diatom testing, the detection of these algae in body tissues to confirm drowning and sometimes identify the water source. It works because diatoms are everywhere in aquatic environments, and they're resilient. They survive decomposition longer than most organic material. If diatoms are found in the lungs but not in deeper tissues, the person was likely dead before entering the water. The heart had stopped, so the algae couldn't circulate. But if diatoms appear in the bone marrow, liver, or kidneys, the person was alive when submerged. The heart was pumping. The drowning was real. The species of diatom can sometimes pinpoint location. A victim found in a river shows diatoms typical of stagnant pond water. The drowning didn't happen where the body was found. Investigators search upstream for ponds. The diatom match narrows the site, but the test has limits. Not all drownings produce detectable diatom levels. Rapid death, cold water, or minimal inhalation can result in low concentrations. And contamination is possible if the body was in water for an extended period before recovery. Still, when diatoms are present in the right tissues and the species can be identified, the evidence ties the victim to a specific body of water. The algae don't lie about where the drowning occurred. Forensic serology. Blood, saliva, semen, sweat, all of it carries markers. Before DNA testing became standard, forensic serology was the primary method for analyzing biological fluids. It still is, in many cases, because serology provides the first screen. It identifies what the fluid is and whether it's worth pursuing further analysis. A stain on fabric. Is it blood? Serology tests confirm it. The fluid reacts with specific chemicals, producing a color change that indicates the presence of hemoglobin. From there, further testing determines if it's human or animal. If human, DNA analysis follows. This is forensic serology, the study and identification of bodily fluids found at crime scenes. It doesn't just confirm presence. It reveals blood type which, while not unique to an individual, narrows possibilities. Type O, A, B, A, B. Each category eliminates or includes potential sources. Saliva contains enzymes unique to oral secretion. Semen contains prostate-specific antigen. Each fluid has biochemical markers that allow serologists to identify it even in mixed or degraded samples. A piece of clothing with multiple stains. Serology determines which is blood, which is saliva, which is something else. The method also detects secretor status. About 80% of people secrete their blood type antigens in other bodily fluids like saliva and sweat. If a suspect is a secretor and their blood type matches saliva found on a victim, the connection strengthens. But serology has limits. It doesn't provide individual identification the way DNA does. Blood type alone doesn't prove someone was at a scene. It only suggests the possibility. That's why serology is often the first step, not the final answer. Still, when biological evidence is present, serology sorts it, categorizes it, and directs the investigation toward the fluids that matter most. It's the filter before the precision work begins. Chain of custody. Evidence means nothing if its integrity is questioned. A fingerprint, a weapon, a blood sample. Any of it can be dismissed in court if the chain of custody breaks. One gap, one unaccounted period, one missing signature, and the defense attacks. Was it tampered with? Was it contaminated? Can we trust it? Chain of custody is the documented chronological record of who handled evidence, when, and why. Every transfer is logged. Every person who touches the evidence signs for it. The item is sealed, labeled, and stored under controlled conditions. If the chain is intact, the evidence is defensible. If it's broken, the case weakens. It starts at the crime scene. The investigator who collects the evidence seals it in a bag or container, labels it with a description, time, date, and their initials. That evidence is then logged into the system. From that point forward, every movement is tracked. If the evidence goes to a lab for testing, the transfer is documented. The lab technician signs for it. When testing is complete, it's returned, and the transfer is logged again. If it's presented in court, the officer who transports it signs it over to the court. Every step recorded. A defense attorney questions the timeline. There's a 6-hour gap where the evidence wasn't accounted for. Who had it? Where was it stored? Could it have been altered? The prosecution has no answer. The chain broke. The evidence, no matter how compelling, loses credibility. But when the chain is unbroken, every movement accounted for, every handler identified, the evidence stands. The fingerprint collected at the scene is the same fingerprint presented in court. The DNA sample wasn't swapped or contaminated. The weapon wasn't mishandled. Chain of custody doesn't prove guilt. It proves the evidence is what investigators claim it is. And without that proof, the evidence is just an object with a story no one can verify. Mitochondrial DNA Analysis. Nuclear DNA degrades. Hair without a root, old bones, teeth from remains decades old. Standard DNA testing often fails. The sample is too degraded, the genetic material too fragmented. But mitochondrial DNA persists. Unlike nuclear DNA, which is inherited from both parents and exists in the cell nucleus. Mitochondrial DNA comes only from the mother and resides in the mitochondria, the cell's energy producers. Each cell contains hundreds of mitochondria, meaning there are far more copies of mitochondrial DNA than nuclear DNA. That redundancy makes it more likely to survive when tissue degrades. This is mitochondrial DNA analysis, the examination of maternally inherited genetic material when nuclear DNA is unavailable. It doesn't provide the same level of individual identification. Mitochondrial DNA is shared among all maternal relatives, siblings, cousins, anyone descended from the same maternal line. But it narrows the field significantly. A skeleton is found, decades old. Nuclear DNA is unrecoverable. But mitochondrial DNA extracted from bone or teeth is intact. Investigators compare it to samples from potential relatives. A match confirms the maternal lineage. The remains belong to someone from that family line. The method also works with hair. A single strand without the root, previously useless for nuclear DNA testing, contains mitochondrial DNA in the shaft. A hair found at a crime scene overlooked for years becomes viable evidence. But the limitation is clear. Mitochondrial DNA doesn't identify one person. It identifies a lineage. In a criminal case, that means it can exclude suspects but not definitively convict. In missing persons cases, it can return remains to a family even when nuclear DNA has long since degraded. When time, decay, or damage erases nuclear DNA, mitochondrial DNA remains. It's the genetic backup, the evidence that persists when everything else fades. Facial approximation. Unidentified remains. No missing person match. No dental records. No fingerprints. Just a skull weathered and nameless. Facial approximation gives it a face. It's not a photograph. It's an educated reconstruction, built from the skull structure and guided by anatomical averages. Tissue depth charts based on population studies indicate how much soft tissue covers each part of the face. The forehead, the cheeks, the chin. Each has a predictable thickness based on age, sex, and ancestry. This is facial approximation, also called facial reconstruction, the process of creating a likeness from skeletal remains to aid identification. Clay, digital modeling, or a combination of both recreates the face that once covered the bone. The skull provides the foundation. Eye sockets determine eye placement. The nasal opening suggests nose shape, though cartilage doesn't survive, so the reconstruction is an approximation. Cheekbones, jawline, brow ridge, all of it guides the placement of tissue. But there are limits. Hair, eye color, facial hair expression. None of that is preserved in bone. The approximation shows a possible appearance, not a definitive one. The goal is recognition, not replication. Someone who knew the person might see the reconstruction and think, that could be them. A skull is found in a remote area. Investigators have no leads. A forensic artist creates a facial approximation. It's published. A family sees it and recognizes features similar to a relative who disappeared years ago. DNA testing confirms the identity. The approximation didn't prove who the person was, but it gave investigators a direction. The face isn't exact. It's an estimate, but when remains have no name and no one is looking for them, facial approximation turns a skull into someone people might remember. It gives the dead a chance to be recognized and, with that recognition, identified. Forensic ballistics. 2 bullets. One from the crime scene, one fired from a suspect's gun in a controlled test. Under magnification, the markings align. Grooves etched by the barrel's rifling match perfectly. Striations left by microscopic imperfections in the metal overlay with precision. The gun that fired the test round is the gun that fired the fatal shot. Firearms leave signatures. Every barrel has unique manufacturing flaws and wear patterns. When a bullet travels through, it picks up those marks. The rifling, the spiral grooves cut into the barrel to spin the bullet and stabilize its flight, creates a pattern. The number of grooves, their width, their direction, all of it transfers to the bullet's surface. This is forensic ballistics, the examination of firearms, ammunition, and the marks they leave. It's not just about matching bullets to guns. It's about understanding trajectories, determining shooting distance, and reconstructing the mechanics of how a shooting unfolded. Firing pin impressions are equally distinctive. When the trigger is pulled, the firing pin strikes the primer at the base of the cartridge, igniting the gunpowder. That strike leaves a mark. The shape, depth, and position of the impression are specific to the gun. Ejected casings carry additional marks from the breech face and the ejector mechanism. Each contact point creates a pattern unique to that firearm. Distance matters. Close-range shots leave gunpowder residue and stippling on the target. The closer the gun, the denser the pattern. At contact range, the muzzle pressed against skin or fabric, the gases from the explosion create distinctive tearing and burning. At a distance, those markers disappear, leaving only the bullet wound. Trajectory analysis reconstructs the shooter's position. Bullet holes in walls, windows, bodies. Each one provides an angle. String or laser rods trace the path backward, revealing where the shooter stood. The height of the entry wound, the downward or upward angle, the sequence of shots. All of it maps the event. A suspect claims the shooting was accidental, the gun misfired. Ballistics analysis shows the trigger had to be pulled with deliberate force. The angle of entry contradicts the suspect's version. The bullet's path tells a different story. The gun doesn't lie. The marks it leaves are reproducible, consistent, and permanent. Fiber comparison. A single thread on a victim's clothing. Under a microscope, the color, thickness, and weave match fibers from a suspect's jacket. Not similar. Identical. Fibers transfer. Sit on a couch and fibers from the fabric cling to your clothes. brush against someone in a struggle, and fibers exchange. They're invisible to the casual observer, but undeniable under magnification. Fiber comparison examines textile evidence to link people, places, and objects. Every fabric has characteristics. Natural fibers like cotton and wool have distinct cellular structures. Synthetic fibers like polyester and nylon show specific chemical compositions and cross-sectional shapes. Dye type, weave pattern, manufacturing technique. Each adds a layer of specificity. When fibers are recovered from a crime scene, they're compared to known samples. A fiber found on a victim is examined alongside fibers from a suspect's clothing. If they match in color, composition, diameter, and structure, the connection is established. The likelihood that two unrelated sources would produce identical fibers in all characteristics is small. But fibers alone don't prove contact. Mass-produced textiles mean thousands of garments share the same fiber characteristics. A blue polyester fiber could come from any number of jackets, car seats, or blankets. That's why fiber evidence is strongest when combined with other evidence. A suspect denies ever being in the victim's car. Fibers from the car's upholstery are found on the suspect's pants. Fibers from the suspect's jacket are found on the car seat. The transfer went both ways. The contact happened. Fibers also reveal sequence. If fibers from a suspect's clothing are found underneath the victim's blood, the suspect was there before the bleeding started. If they're on top of the blood, contact occurred after. Fibers are fragile. They fall off, degrade, wash away. But when they're recovered fresh and the comparison is thorough, they document contact that no one can deny. Livor mortis interpretation. The body lies face down, but the discoloration is on the back. The blood pooled on the wrong side. The position doesn't match the lividity. Someone moved the body after death. When the heart stops, gravity takes over. Blood settles into the lowest parts of the body, creating dark purplish patches called livor mortis. If a person dies lying on their back, the lividity appears on the back, shoulders, and buttocks. If they die face down, it appears on the face, chest, and abdomen. Livor mortis develops within the first few hours after death. Initially, the discoloration is faint and shifts if the body is moved. But after several hours, the blood fixes in place. Press on the skin, and the color doesn't blanket. The lividity is locked. This is livor mortis interpretation, the analysis of post-mortem blood pooling to determine body position at the time of death and detect movement after death. It's one of the clearest indicators that a scene has been staged. A victim is found slumped in a chair. Lividity is present on the back and buttocks, consistent with a seated position. The scene appears undisturbed. But a closer look reveals faint secondary lividity on the left side, barely visible but present. The body was lying on its side for a period before being moved to the chair. The scene was altered. Livor mortis also helps estimate time of death. It begins within the first hour, becomes noticeable within a few hours, and fixes after 8 to 12 hours, depending on conditions. If lividity is fully developed and fixed, the person has been dead for at least several hours. If it blanches under pressure, death was more recent. But livor mortis has limits. It doesn't provide a precise time, only a range. Temperature, body weight, and cause of death all influence the rate. Still, when the pattern doesn't align with the position, the discrepancy is clear. The body was moved, and once that's established, the original scene is gone. What investigators see is what someone wanted them to see. Algor mortis estimation. The body is still warm. Not warm like a living person, but warmer than the surrounding air. Investigators take the core temperature. The calculation begins. After death, the body cools. The rate is predictable under stable conditions, roughly 1.5 degrees Fahrenheit per hour. If the body temperature is measured and the ambient temperature is known, time of death can be estimated. This is Algor mortis estimation, the use of body temperature to determine post-mortem interval. It's one of the earliest methods forensic investigators use when a body is discovered. and it's most accurate in the first 24 hours. The formula is straightforward. Normal body temperature is around 98.6 degrees. Subtract the measured body temperature, divide by the cooling rate, and the result is the approximate time since death. A body at 90 degrees in a room at 70 degrees has been dead for roughly 6 hours. But the calculation isn't simple in practice. Cooling rate varies. A body in cold water cools faster. A body in heavy clothing cools slower. A body in direct sunlight warms, complicating the reading. Obese individuals retain heat longer. Thin individuals cool faster. Cause of death matters too. Fever at the time of death raises the starting temperature. Hypothermia lowers it. Environmental factors complicate further. Wind, humidity, surface the body rests on. All of it affects heat transfer. That's why forensic pathologists take multiple temperature readings and account for conditions before making an estimate. A suspect claims the victim was alive at noon. The body is found at 6 in the evening with a core temperature of 91 degrees. Given the ambient temperature and the victim's build, the cooling rate suggests death occurred around 10 in the morning. The timeline contradicts the alibi. Algor Mortis isn't a perfect clock. After 24 hours, the body reaches ambient temperature, and the method loses utility. But in the crucial early window, temperature provides a timeline that narrows possibilities and challenges false narratives. Rigor mortis assessment. The body is stiff. Arms locked, jaw clenched, fingers curled. Rigor mortis has set in. But it won't last. Within hours, the stiffness will fade, and the body will go limp again. Rigor mortis, the stiffening of muscles after death, follows a predictable sequence. It begins in the smaller muscles of the face and jaw, then spreads to the larger muscles of the limbs and torso. The progression takes several hours. Full rigor, where the entire body is stiff, typically develops within 12 hours under average conditions. But rigor doesn't stay. After reaching its peak, it gradually releases. The muscles relax in the same order they stiffened. By 24 to 36 hours post-mortem, rigor is usually gone, though environmental factors and physical condition alter the timeline. This is rigor mortis assessment, the examination of muscle stiffness to estimate time of death and detect unusual circumstances. It's a rough tool, not a precise clock, but it provides context when combined with other post-mortem indicators. Temperature affects rigor. Heat accelerates it. Cold delays it. A body in a warm room develops rigor faster than one left outdoors in winter. Strenuous activity before death, like a struggle, depletes muscle energy stores and cause rigor to set in earlier and more intensely. A victim is found with full rigor mortis. Investigators estimate death occurred 10 to 12 hours prior, but witness statements place the person alive within the last 6 hours. Something doesn't align. Further investigation reveals the body was moved from a cold environment to a warm one, accelerating rigor. The timeline adjusts. Rigor also reveals position at death. If a body is found seated but rigor developed while the body was lying flat, the stiffness won't match the current position. The arms and legs hold the shape of the original posture. Movement after death becomes obvious, but rigor can be broken. Force applied to a stiffened limb can overcome the stiffness, though the muscle won't re-stiffen. If rigor is absent when it should be present, or present when it should be gone, the timeline shifts and the investigation adapts. Rigor mortis marks time, and when the stiffness doesn't match the story changes. Soil forensics, mud on a shoe, dirt under fingernails, a smear of clay on the undercarriage of a car. Soil carries a signature. Different locations, different compositions. Sand, silt, clay, mineral content, pollen, plant fragments. Each deposit is distinct. A suspect claims they've never been to the burial site. Soil samples from their vehicle tell a different story. The mineral composition, the particle size distribution, the presence of specific pollen species. All of it matches soil from the scene. The soil traveled with them. This is soil forensics, the analysis of soil and sediment to link suspects and objects to locations. It works because soil varies even over short distances. Soil from a river bank differs from soil 100 yards inland. Soil from one side of a field differs from soil on the other side. Forensic geologists examine color, texture, and composition. They identify minerals under a microscope, analyze organic content, and test pH levels. Pollen embedded in the soil narrows the geographic range further. Certain plants grow in specific regions. If the soil contains pollen from a species that only grows in one area, the origin is pinpointed. A body is found in a remote forest. Investigators recover soil from the victim's clothing and compare it to soil from various locations. The match comes from a trail several miles from where the suspect lives. But soil matching that same composition is found in the suspect's car trunk. The connection is direct. Soil also reveals sequence. Layered deposits on a shovel show where it was used first, second, third. If soil from a burial site is found beneath soil from a different location, the shovel was used at the burial site before being used elsewhere. But soil forensics has limits. Generic soils, common across wide areas, offer less specificity. Urban environments where soil is mixed and redistributed complicate analysis. And contamination is always a risk. Soil transfers easily and doesn't always indicate intent. Still, when the soil is distinctive and the comparison is thorough, it places a person, vehicle, or object at a location they claimed they'd never been. The dirt doesn't forget where it came from. Forensic document examination. The signature looks right, same loops, same slant, same pressure. But under magnification, the hesitation marks appear. Tiny stops where the pen paused. Breaks in the stroke where a forger lifted and repositioned. A genuine signature flows. This one was traced. Every handwritten document carries markers. Pen pressure, writing speed, letter formation, spacing, these patterns are individual. Forgers copy the shape, but they can't replicate the unconscious rhythm of someone's natural writing. Document examination goes beyond handwriting. It analyzes paper, ink, printer characteristics, indentations, alterations, and erasures. A will is contested. The signature is questioned. Examiners compare it to known samples. The stroke patterns don't align. The trimmer is artificial, not the natural shake of age. The document is fraudulent. Indented writing reveals hidden text. Someone writes on a notepad, tears off the top sheet, and discards it. But the pressure transferred to the page beneath. Oblique lighting or electrostatic detection makes the indentations visible. A note thought destroyed reappears on the blank sheet below it. Alterations show themselves under examination. A number is changed on a contract. The original ink is covered with correction fluid, and a new number is written over it. Infrared or ultraviolet light reveals the difference. The two inks don't match. The document was modified after signing. Typewriters and printers leave unique marks. Each typewriter has slight misalignments in its keys. Each printer has defects in its drum or inkjet nozzles. A ransom note typed on a specific machine can be matched to that machine. The imperfections are consistent and traceable. A suspect denies writing a threatening letter. The handwriting is compared to known samples. The letter formations match. The connecting strokes align. The variation in pressure is identical. The letter came from that person's hand, even if the words were disguised. Documents don't just carry information. They carry the trace of who created them. Ink dating. A contract is signed dated 2 years ago, but the ink tells a different story. Chemical analysis shows the ink formulation wasn't manufactured until last year. The document is backdated. Ink changes over time. Solvents evaporate. Chemical components degrade. Fresh ink behaves differently than old ink under analysis. By measuring the volatile compounds still present and comparing them to known degradation rates, investigators can estimate when the ink was applied. Different ink formulations have different chemical signatures. Manufacturers change recipes, discontinue certain dyes, introduce new solvents. If a document is dated before a particular ink formulation existed, the date is false. Ink dating also examines the intersection of strokes. If a signature crosses a printed line, which came first? The ink on top shows less absorption into the paper. The ink beneath has soaked in. The layering reveals sequence. If a signature sits on top of text that was supposedly written later, the timeline is wrong. But ink dating has limits. It works best on recent documents, where volatile compounds are still detectable. Older documents lose those markers. Environmental factors affect degradation rates. Heat accelerates it. Cold slows it. Humidity, light exposure, storage conditions, all of it complicates the estimate. A disputed contract surfaces in litigation. The plaintiff claims it was signed 5 years ago. Ink analysis shows the document was created within the last 18 months. The claim collapses. Ink doesn't lie about its age. And when the chemistry contradicts the date, the document's authenticity is gone. DNA mixture interpretation. 3 people touched the same surface. Their DNA mixed. The sample isn't clean. It's a blend of genetic material from multiple contributors, and separating it isn't straightforward. DNA mixtures are common. A weapon handled by both victim and attacker. A doorknob touched by several people. Clothing worn by one person, then grabbed by another. The genetic profiles overlap, creating a composite that has to be untangled. Interpreting mixtures requires statistical analysis. Software calculates probability that a specific individual contributed to the sample. Major contributors, those who left more DNA, are easier to identify. Minor contributors, those who left trace amounts, are harder to isolate. The ratio matters. If one person's DNA is 10 times more abundant than another's, the major profile is clear. But if the contributions are roughly equal, interpretation becomes complex. Alleles overlap. Peaks on the genetic profile merge. Determining who contributed what requires careful calculation and conservative interpretation. A knife used in an assault contains DNA from 2 people. The victim's profile is the major contributor. The attacker's profile is present but faint. Analysts calculate the likelihood that the suspect's DNA is in the mixture. The match is statistically significant. The suspect handled the knife. But mixtures introduce uncertainty. Defense attorneys challenge the interpretation. Could the DNA have come from someone else? Could contamination have occurred? Mixture analysis is probabilistic, not absolute. That's why analysts present results as likelihoods, not certainties. When the mixture is simple and the contributors are few, interpretation is reliable. When the mixture is complex, with multiple contributors and degraded samples, the conclusions become cautious. The DNA is there, but sorting it definitively is harder. Still, when the statistics support it and the major contributors are clear, mixtures provide evidence that places multiple people at the same point of contact. Forensic genealogy. A decades-old murder. No suspect. DNA from the crime scene but no match in the criminal database. Traditional forensic methods store. Then investigators turn to genealogy. They upload the DNA profile to a public genealogy database, the kind people use to trace family trees. The system searches for partial matches, distant relatives who share segments of DNA, a third cousin, a second cousin once removed, people who've never met the suspect but share a common ancestor. From those distant relatives, genealogists build a family tree. They trace lineages, follow birth records, track marriages and relocations. The tree branches out, then narrows back down. Eventually, it points to a small group of individuals who could be the source. Investigators focus on those names. One matches the age, location, and circumstances. DNA collected from that person confirms it. The cold case breaks. This is forensic genealogy, the use of genetic genealogy databases and family tree construction to identify suspects or victims. It doesn't rely on the suspect's DNA being in a criminal database. It relies on their relatives voluntarily uploading their own DNA for ancestry purposes. The method has solved cases that went cold for decades. The Golden State Killer. Unidentified remains, child abductions from the past. Cases where traditional DNA databases offered no leads. But forensic genealogy raises questions. The people in the database didn't consent to their genetic information being used in criminal investigations. They uploaded it to learn about their heritage, not to implicate a distant relative. Privacy concerns linger. Some databases have restricted law enforcement access. Others allow it under certain conditions. Still, when traditional methods fail and the DNA is available, forensic genealogy offers a path. It turns genetic data into a map that leads back to individuals who thought they'd never be found. The family tree becomes the investigative tool, and distant relatives, unknowingly, provide the connection. Bite mark comparison. A bite mark on skin. The pattern of teeth impressions analyzed, measured, compared to a suspect's dental mold. For years, bite mark evidence sent people to prison. Then the science unraveled. Skin isn't stable. It stretches, swells, bruises, and distorts. A bite leaves an impression, but that impression changes. The mark photographed hours after the injury looks different than it did immediately after. The skin's elasticity makes precise measurement unreliable. Teeth are individual, but bite marks aren't fingerprints. The same person biting the same surface with the same force won't leave identical marks every time. Angle, pressure, movement. All of it alters the pattern. Overlay analysis, where a suspect's dental mold is placed over a photograph of the bite, became the standard method. But the comparisons were subjective. Different examiners reached different conclusions on the same evidence. DNA changed the field. Saliva left during a bite can be tested. The genetic profile is far more reliable than the mark itself. If DNA from the bite matches the suspect, the connection is strong. If it doesn't, the bite mark analysis becomes irrelevant. Courts have grown skeptical. Convictions based solely on bite mark testimony have been overturned. The National Academy of Sciences questioned the scientific foundation. The method isn't banned, but it's no longer accepted uncritically. Prosecutors need corroborating evidence. Defense attorneys challenge the reliability. A suspect's teeth are compared to a mark on a victim. The examiner testifies they match. But DNA from the bite excludes the suspect. The bite mark evidence collapses. The person walks free. Bite marks still appear in cases, but they're treated cautiously. The pattern might suggest something, but without DNA or other evidence, the mark alone doesn't convict. The science that once seemed certain is now understood as fallible. Fracture matching. A headlight is shattered at a hit-and-run scene. Glass fragments scatter across the pavement. Days later, investigators find a suspect's vehicle with a broken headlight. They collect the remaining glass from the car. Under examination, the edges of the fragments from the scene align perfectly with the edges of the glass still in the vehicle. The fit is exact. The glass came from that car. Fracture matching works because breaks are unique. When glass, plastic, bone, or metal fractures, the break pattern is random. No two fractures are identical, but pieces from the same object fit together like a puzzle. The edges align. The surface textures match. The fracture lines continue across the gap. Paint chips work the same way. A car sideswiped a pole. Paint transfers to the pole. Paint is missing from the car. Investigators compare the chip to the car's damaged area. The layers match. The color sequence is identical. The chip fits the void. The car hit the pole. Bone fractures reveal trauma. A skull is fractured. Investigators recover a weapon. They compare the fracture pattern to the shape of the weapon's edge. The curvature matches. The width aligns. The weapon that caused the fracture is identified. Torn materials follow the same principle. A piece of fabric is ripped from a jacket during a struggle. The torn edge is compared to the jacket. The weave pattern continues. The tear lines match. The fabric came from that garment, but fracture matching requires clean breaks and minimal damage. If fragments are crushed, worn, or degraded, the fit becomes unclear. And not all fractures are distinctive enough to provide a definitive match. Generic breaks in common materials offer less certainty. Still, when the fracture is fresh and the pieces are intact, the match is undeniable. The edges either fit or they don't. And when they fit, the connection between object and scene is direct. The fragment didn't just come from a similar source. It came from that specific object. Tape lift collection. The surface looks clean, but press adhesive tape against it, peel it off, and the invisible becomes visible. Hair strands, fibers, dust particles, pollen, fragments too small to see with the naked eye, now captured on the tape's sticky surface. Crime scenes are littered with microscopic evidence. A suspect sits on a couch, and fibers from their clothing transfer. They walk across a floor, and soil from their shoes sheds. They touch a wall, and skin cells remain. Most of it is invisible until collected. Tape lifting captures these traces. The tape is pressed firmly onto the surface, then removed and sealed onto a transparent backing. Under magnification, the collected material is examined. Each fiber, each particle, each fragment is analyzed and compared to known samples. A burglar enters through a window. They cross the living room, rifle through drawers, exit through the back door. Tape lifts from the floor near the window recover fibers matching the suspect's jacket. Tape lifts from the drawer handles recover soil consistent with the suspect's shoe trades. The path through the house is documented in microscopic transfers. The method works on fabric, hard surfaces, skin, even adhesive residues. Tape lifts from a victim's clothing recover foreign fibers. Tape lifts from a suspect's hands recover gunshot residue. The tape doesn't discriminate. It collects everything it contacts. But tape lifting is indiscriminate. It captures background material as well as relevant evidence. A fiber recovered from a scene could have been there for days, transferred by someone unrelated to the crime. That's why context matters. The more specific the location and the fresher the scene, the stronger the connection. When the tape is lifted and the evidence is there, it confirms contact. Something from one place ended up in another, and once collected, that microscopic record is preserved. Vacuum metal deposition. Fingerprints on plastic bags, metal foils, smooth non-porous surfaces that powder won't adhere to. These prints remain invisible under traditional methods. But vacuum metal deposition makes them appear. The process happens in a vacuum chamber. The item is placed inside and the air is removed. Gold is heated until it vaporizes, coating the surface in an ultra-thin layer. Then zinc is vaporized, depositing over the gold. Where fingerprint oils are present, the metals don't adhere uniformly. The print stands out in contrast, visible against the background. The method is extraordinarily sensitive. Prints that are days old, prints on surfaces previously thought unworkable, prints contaminated or degraded, all of them can be developed through metal deposition. The gold layer highlights ridges with precision that powder can't match. A piece of evidence is submitted. Traditional powder techniques failed. No prints were visible. The item is processed through vacuum metal deposition. Prints appear clear and detailed on a surface that seemed barren, but the process is expensive and time-consuming. It requires specialized equipment and controlled conditions. That's why it's reserved for high-priority cases where other methods have failed. When the evidence is critical and the surface is difficult, vacuum metal deposition is the option of last resort. A plastic bag used in a kidnapping. No visible prints. Powder doesn't work. The bag is processed through metal deposition. A partial print appears. It matches a suspect. The connection is made. The method doesn't just find prints. It finds prints that shouldn't exist anymore, prints that were invisible until metal made them permanent. Accelerant detection. Fire destroys evidence. It burns away fingerprints, DNA fibers, most of what investigators rely on. But fire also creates evidence. When an accelerant like gasoline or lighter fluid is used to start or spread a blaze, chemical traces remain even after the flames are out. Accelerants don't burn completely. Residues soak into porous materials. Wood, carpet, concrete. Even after intense heat, trace amounts linger. Investigators collect samples from suspected pore patterns, areas where the fire burned hotter or spread faster. Those samples are sealed in airtight containers to preserve volatile compounds. In the lab, the samples are heated. The vapors are analyzed using gas chromatography, a technique that separates chemical components. Each accelerant has a distinct chemical fingerprint. Gasoline, kerosene, lighter fluid, paint thinner. Each shows a unique pattern. If that pattern appears in the sample, the accelerant is identified. A house fire is ruled suspicious. The burn pattern suggests multiple points of origin. Samples from the floor near those points are tested. Gasoline residues are detected. The fire was deliberately set. But accelerant detection has complications. Household materials release similar compounds when they burn. Plastics, cleaning products, even carpet padding can produce chemicals that mimic accelerants. That's why context matters. The presence of accelerant residues combined with burn patterns, witness statements, and other evidence builds the case. A suspect denies involvement, but accelerant residues on their clothing, matching the residues at the fire scene, contradict the denial. The chemicals traveled with them. Fire erases most evidence, but the accelerant that started the fire leaves a chemical signature that heat can't destroy. And once detected, it marks the fire as arson. Glass fracture analysis. A window is broken. Radial cracks spread outward from the point of impact. Concentric cracks circle around it. The pattern reveals which side the glass was struck from, the direction of the force, and sometimes the sequence of impacts. Glass fractures follow predictable patterns. When something strikes glass, it creates a cone-shaped fracture that widens away from the impact point. The wider part of the cone faces the side opposite the strike. By examining the edges of the fracture, investigators determine which side the force came from. Radial cracks form first, spreading outward like spokes on a wheel. Concentric cracks form next, connecting the radial cracks in roughly circular patterns. If multiple impacts occur, the cracks from the second impact stop when they meet cracks from the first. The sequence is locked in the glass. A burglary scene. A window is shattered. The fracture pattern shows the impact came from outside. The radial cracks confirm force was applied from the exterior. The claim that someone inside accidentally broke it doesn't hold. Glass fragments also reveal impact angle. High-velocity impacts like bullets create different fracture patterns than low-velocity impacts like thrown rocks. The size and distribution of fragments indicate the force involved. A windshield is struck by a bullet. The entry side shows a clean, small hole. The exit side shows a larger, irregular opening with radial cracks spreading outward. The direction of fire is clear. But glass analysis has limits. If the glass is tempered or laminated, fracture patterns differ. Environmental stress, prior damage, or manufacturing flaws complicate interpretation. Still, when the glass is standard and the fractures are fresh, the pattern speaks. The break wasn't random. It tells the story of what hit it, from which side, and in what order. Microtrace Recovery. The suspect claims they've never been in the victim's car, but embedded in the fibers of their jacket, microscopic glass fragments are recovered. The refractive index matches the car's shattered window. The suspect was there when the glass broke. Microtraces are fragments so small they're invisible without magnification. Glass particles, metal shavings, paint chips, concrete dust, plant material. Each one carries identifying characteristics. When recovered and analyzed, they link people to places, objects to events. Recovery requires precision. Tape lifts capture surface material. Vacuuming with filtered collectors gathers particles from clothing and surfaces. Scraping tools retrieve material from under fingernails or embedded in fabric. Each method targets different trace types. Once collected, the fragments are examined. Glass particles are measured for refractive index and elemental composition. Paint chips are analyzed for layering and chemical makeup. Metal fragments are tested for alloy composition. Each characteristic narrows the source. A suspect denies being at a construction site where a crime occurred. Concrete dust on their shoes matches the specific mix used at the site. The dust didn't come from just any construction area. It came from that location. Microtraces also reveal sequence and contact. If glass from a broken headlight is found under blood on a hit and run victim's clothing, the glass was there first. The impact broke the headlight before the bleeding started. The sequence of events is documented in layers. But microtraces are fragile. They fall off, wash away, transfer to other surfaces. The window for recovery is short. That's why investigators act quickly, sealing clothing and objects before traces are lost. When microtraces are recovered and matched, they create connections that can't be explained away. The particles didn't appear by coincidence. They transferred during contact, and they stayed long enough to be found. Cell site analysis. A phone doesn't just make calls. It constantly communicates with cell towers, even when idle. Every tower contact is logged. The time, the tower location, the signal strength, all of it creates a record. That record becomes a map of where the phone was and when. Cell towers have coverage areas. When a phone connects to a tower, it's somewhere within that range. The signal strength indicates distance. Stronger signals mean closer proximity. By analyzing which towers a phone contacted and in what sequence, investigators reconstruct movement. A suspect claims they were at home during a crime. Cell site data shows their phone connecting to towers near the crime scene at the time of the incident. The alibi doesn't hold. The phone was there, and the phone was with the suspect. The method isn't precise. A tower's coverage area can span miles, especially in rural regions. A phone connecting to a specific tower places it within a zone, not at an exact address. But when combined with other evidence, witness statements, surveillance footage, GPS data, the pattern sharpens. Multiple towers refine the estimate. If a phone connects to 3 towers simultaneously, analysts triangulate. The overlapping coverage areas narrow the possible location. The phone was within a smaller zone, closer to the intersection of the ranges. Historical data maps patterns. A phone that regularly connects to towers near a suspect's home, workplace, and a specific meeting point establishes routine. When that phone connects to towers near a crime scene on the day of the crime, the deviation stands out. But cell site data isn't foolproof. Towers can hand off calls unpredictably. Coverage areas shift with network load. And having a phone near a location doesn't prove the owner was there. Phones are stolen, borrowed, left behind. Still, when the timing aligns, the tower sequence tracks movement, and the pattern fits the crime. Cell site data provides a timeline that's hard to ignore. The phone left a trail. And where the phone went, the person followed. Forensic phonetics. A ransom call. The voice is disguised, the words distorted. But the way certain sounds are pronounced, the rhythm of speech, the subtle accent markers, these don't disappear. Voice analysis reveals patterns the speaker can't fully hide. Everyone speaks with distinctive characteristics. Pitch, intonation, speech rate, vowel pronunciation. These combine into a vocal fingerprint. Even when someone tries to alter their voice, traces of their natural pattern remain. Forensic phonetics analyzes recordings to identify speakers or detect manipulation. The process examines acoustic features, frequency resonance, stress patterns. A spectrogram visualizes sound waves, showing how speech unfolds over time. Patterns emerge. Repeated phrases across different recordings reveal consistency. A suspect's known speech is compared to the disguised voice. Certain phonetic traits align. But voice analysis isn't as definitive as fingerprints. People can alter pitch, slow their speech, adopt accents. Background noise, poor recording quality, and emotional state affect the voice. That's why forensic phonetics offers probabilistic conclusions, not absolute identification. A threatening call is traced. The caller used a voice modulator. But speech patterns, the way certain words are emphasized, the pauses between phrases, these match a suspect's natural rhythm. The technology changed the sound, but not the underlying structure. Accent analysis also aids investigations. A speaker's regional accent, even faint, reveals geographic origin. Linguistic features narrow the search. A caller claims to be from one region. Phonetic analysis detects markers from a different area. The claim is false. Voice isn't just sound. It's a pattern built over a lifetime of speaking. And when recordings are compared, those patterns either match or they don't. Image authentication. The photo looks real. The lighting is right. The shadows fall correctly. But digital analysis reveals inconsistencies. The metadata shows the image was edited. Certain areas were cloned from elsewhere in the frame. The photo is manipulated. Digital images leave traces when altered. Compression artifacts, lighting mismatches, perspective errors. These signal tampering. Forensic image analysis detects these anomalies. Metadata, the information embedded in image files, records camera model, date, time, GPS coordinates, and software used. If the metadata shows an image was opened in editing software, the file was modified. If the timestamp doesn't match when the photo was claimed to have been taken, the timeline is suspect. Error level analysis highlights areas with different compression rates. When a portion of an image is copied and pasted from another source, that section compresses differently than the original. The mismatch is visible under analysis. Shadows and lighting also betray alterations. If light sources in different parts of the image come from inconsistent angles, elements were added or moved. A suspect submits an alibi photo showing them at a location during the crime. Image analysis reveals the photo was taken days earlier and the date metadata was altered. The alibi collapses, but detection has limits. Sophisticated editing minimizes detectable artifacts. High-resolution images and careful manipulation reduce inconsistencies. As technology advances, so do the methods for creating undetectable fakes. Still, when analysis reveals tampering, the image loses credibility. The photo isn't evidence of reality. It's evidence of manipulation. Forensic osteology. Bones tell age. A skull's sutures, the way the bones of the skull knit together, fuse progressively through life. In young individuals, the sutures are open. In older individuals, they close. The degree of fusion estimates age. Teeth also age. Wear patterns, enamel erosion, root development. These change predictably. In children, tooth eruption follows a timeline. By examining which teeth are present and their stage of development, age is narrowed to a range. Long bones grow until adulthood. Growth plates, visible in X-rays, close at specific ages. If the plates are still open, the person was young. If closed, adulthood was reached. The pattern is consistent enough to estimate age within a few years. But osteology is about more than age. Bones reveal sex, ancestry, stature, and trauma. Healed fractures show old injuries. Cut marks on bone indicate violence. Pathological changes reveal disease. A skeleton is found. The pelvis structure suggests female. The skull features indicate European ancestry. Tooth wear and sutural closure place age between 30 and 40. Long bone measurements estimate height around 5'6". The profile narrows the search for a missing person. Trauma analysis identifies cause of death. A depressed skull fracture indicates blunt force. The shape and size of the fracture suggest a cylindrical object, possibly a bat or pipe. The injury was severe enough to be fatal. But bones don't always answer every question. Soft tissue damage doesn't survive. Exact time of death becomes imprecise once skeletonization occurs. An individual variation means estimates are ranges, not certainties. Still, when flesh is gone and identity is lost, bones remain. and they carry enough information to rebuild a profile, identify trauma, and point investigators toward answers. Biometric comparison. Iris patterns, facial geometry, vein structure in the hand. Each person's biometric markers are unique. When captured and analyzed, they confirm identity with extraordinary precision. Facial recognition maps distances between eyes, nose width, jawline contours. Algorithms convert these measurements into a digital template. That template is compared to databases. If a match exists, identity is established. Security footage captures a suspect's face. Facial recognition searches millions of records and returns a name. Iris scanning is even more precise. The colored ring around the pupil has patterns, furrows, ridges, freckles, that don't change over a lifetime. An iris scan captures these details. The probability of two people having identical iris patterns is astronomically low. When a scan matches a database entry, the identification is nearly certain. Vein pattern recognition analyzes the unique arrangement of veins beneath the skin. Infrared light reveals the pattern, which is then digitized. Like fingerprints, vein patterns don't duplicate. The method works even if skin is damaged or aged. But biometric systems have weaknesses. Facial recognition struggles with poor lighting angles or disguises. Aging, injury, and surgery alter facial features, reducing match accuracy. Iris scans require cooperation and close-range imaging. And all biometric databases raise privacy concerns. Once enrolled, a person's biometric data exists indefinitely in a system they don't control. Still, when conditions are favorable and the match is strong, biometrics provide identification that's harder to fake than documents or passwords. The body itself becomes the credential. And when the scan matches the record, the person is confirmed. Chemical profiling. Drugs aren't uniform. Different batches, even from the same source, have slight chemical variations. Manufacturers use different cutting agents, solvents, and synthesis methods. These differences create a chemical signature. When drugs are seized, profiling identifies their origin. Explosives work the same way. Commercial explosives contain tagans, chemical markers added during manufacturing to aid tracing. Homemade explosives have residue patterns specific to their components. The chemical profile links an explosive device to its source materials. Paint, adhesives, plastics, each product has a formulation. Chemical analysis identifies the components. A paint chip from a hit-and-run vehicle is profiled. The pigment mixture matches a specific automotive brand and year. The search narrows. Soil chemistry also profiles location. Mineral content, pH, organic composition. These vary by region. Soil on a suspect's shoes is profiled and compared to the crime scene. The chemical signature matches. The suspect was there. But chemical profiling has limits. Mass-produced items with identical formulations don't offer unique signatures. Generic chemicals provide less specificity, and contamination or degradation can alter profiles, complicating analysis. Still, when the profile is distinctive and the comparison is thorough, chemical signatures link materials to sources. The substance carries a history, and profiling reads it. Scene reconstruction. The room is chaotic. Blood on the walls, furniture overturned, shell casings on the floor. It looks random. But piece by piece, the scene reveals order. Bloodstain patterns show where the victim stood when struck. Bullet trajectories trace back to the shooter's position. The scatter of debris indicates the sequence of impacts. The chaos has a story, and reconstruction tells it. Every element in a crime scene is a data point. The angle of blood spatter, the depth of a footprint, the position of a body, the direction of broken glass. Each one contributes to the timeline and the mechanics of what happened. Reconstruction begins with documentation. Photographs from every angle. Measurements of distances and heights. Notes on every object's position. Once the scene is recorded, analysis begins. Bloodstain patterns are traced back to their origin. Bullet holes are connected with trajectory rods. revealing the shooter's location and the victim's position when shot. If a body has been moved, lividity patterns won't match the position. If a weapon was staged, fingerprints or DNA might be absent where they should be present. If the scene was cleaned, Luminol reveals blood residue in places that look spotless. Physical evidence doesn't lie, but it requires interpretation. Experts reconstruct the sequence of events. The first shot, the victim's movement; the second shot, the fall. The timeline locks into place, step by step. A defendant claims self-defense. Reconstruction shows the victim was shot in the back from across the room, not during a close-range struggle. The physical evidence contradicts the narrative. The scene tells the truth the testimony tried to hide. Reconstruction doesn't just solve cases. It disproves false accounts, confirms witness statements, and reveals what happened when no one was watching. The scene is frozen in time, and every mark, every stain, every fragment speaks. The evidence remembers what people forget, distort, or deny. And when the pieces are assembled, the scene reconstructs itself. Trace evidence analysis. A single fiber, a flake of paint, a grain of sand. Fragments so small they pass unnoticed, yet each one tells where someone has been, what they've touched, who they've contacted. Trace evidence doesn't shout, it whispers. But when collected and analyzed, those whispers build a case. Trace evidence is anything transferred during contact. Locard's principle states that every contact leaves a trace. Sit in a car and fibers from the seat transfer to your clothing. Walk through a room and carpet fibers cling to your shoes. Brush against someone and material exchanges. Most of it is invisible without magnification. Analysis begins with collection. Tape lifts capture surface material. Tweezers retrieve individual fibers. Vacuums with filtered collectors gather particles from clothing and objects. Once collected, each trace is examined under microscopy. Fibers are identified by type, color, diameter, and weave. Paint chips are analyzed for layering and chemical composition. Glass fragments are tested for refractive index. A suspect denies being in the victim's apartment. Trace analysis recovers carpet fibers from the suspect's jacket matching the victim's living room carpet. Fibers from the suspect's clothing are found on the victim's couch. The transfer went both ways. Contact occurred, but trace evidence has limits. Generic materials offer less specificity. A blue cotton fiber could come from thousands of sources. That's why trace evidence works best when combined with other evidence. Multiple fiber types matching unusual materials, or bidirectional transfer strengthens the connection. A hit-and-run vehicle is located. Paint transfer on the victim's clothing matches the vehicle's paint in color and layering. Glass fragments embedded in the victim's jacket match the vehicle's broken headlight. Fiber from the victim's coat is found in the vehicle's undercarriage. Each trace alone suggests contact. Together, they confirm it. Trace evidence is fragile. It falls off, washes away, degrades. The window for recovery is short, but when it's collected fresh and analyzed thoroughly, those microscopic fragments document contact that can't be explained away. Forensic linguistics. The ransom note uses specific phrasing, certain grammatical patterns, word choices, punctuation habits. A linguist analyzes the text and identifies markers, regional dialect features, educational level, native language interference. The note was written by someone with a particular linguistic background. The suspect pool narrows. Language is individual. The way someone structures sentences, the words they choose, their spelling errors. These patterns are as distinctive as handwriting. Forensic linguistics examines written and spoken language to identify authors, detect deception, and analyze threatening communications. Authorship analysis compares texts. A suspect's known writing samples are examined alongside the questioned document. Do they use the same sentence structures? The same vocabulary? The same punctuation style? Consistent patterns suggest common authorship. Divergent patterns suggest different writers. Dialect analysis identifies regional or social background. Vocabulary choices, grammatical constructions, and idioms reveal where someone learned to speak. A threatening letter uses phrases common to a specific region. Investigators focus on suspects from that area. Linguistic analysis also detects deception. When people lie in written statements, language patterns shift. Pronouns change. Passive constructions increase. Specificity decreases. The text becomes evasive. Analysts identify these markers and flag inconsistencies. A suspect writes a statement claiming they were uninvolved. Linguistic analysis reveals shifts in pronoun use when describing the critical time frame. The narrative becomes vague. The language pattern suggests avoidance. The statement is inconsistent with truthful recall. But forensic linguistics isn't foolproof. People code switch, altering language based on context. Collaborative writing muddles individual patterns. And linguistic markers are probabilistic, not absolute. Analysis provides direction, not definitive proof. Still, when patterns are strong and the corpus is sufficient, language reveals the writer. The words themselves become evidence, and the way they're arranged exposes who put them there. Forensic toxicology. A sudden death. No visible trauma. No obvious cause. But toxicology reveals the answer. Toxic levels of a substance in the blood. Something that shouldn't be there or something present in lethal concentration. The death wasn't natural. It was poisoning. Forensic toxicology analyzes biological samples. Blood, urine, tissue, hair, for drugs, poisons, alcohol, and chemicals. It determines what substances are present, at what levels, and whether those levels could have caused or contributed to death. Testing begins with screening. Broad tests detect classes of substances, opioids, stimulants, sedatives. If the screen is positive, confirmation testing identifies the specific compound and measures concentration. Different substances require different methods. Alcohol is measured directly. Drugs are detected through immunoassays and confirmed with mass spectrometry. Interpretation requires context. A therapeutic dose of a medication is safe. A toxic dose is dangerous. A lethal dose causes death. But individual tolerance varies. What's lethal for one person might be survivable for another. Toxicologists consider the person's medical history, prescriptions, and circumstances. A victim is found dead with no signs of violence. Toxicology detects high levels of a prescription sedative in the blood. The victim had a prescription, but the concentration is far beyond therapeutic range. The death is ruled an overdose. Whether accidental, suicidal, or homicidal requires further investigation. Toxicology also detects impairment. A driver involved in a fatal crash has blood alcohol above the legal limit. The toxicology report supports a DUI charge. A worker dies in an industrial accident. Toxicology reveals methamphetamine in their system. The substance may have contributed to impaired judgment, but toxicology has limits. Some substances metabolize quickly and become undetectable. Postmortem redistribution can alter concentrations, complicating interpretation. And not all poisons leave clear markers. Still, when toxic substances are detected at levels consistent with harm, toxicology provides answers. The body carries the chemical evidence and analysis reads it. Geolocation Forensics. Every photo taken with a smartphone embeds GPS coordinates. Every social media check-in logs a location. Every credit card transaction records where it occurred. Digital devices don't just capture moments, they map them. And when someone claims they were elsewhere, the digital trail tells a different story. Geolocation Forensics analyzes location data to track movement, verify alibis, and reconstruct timelines. The data comes from phones, vehicles, apps, cameras, and payment systems. Each one creates a record of where someone was and when. Photo metadata is the most direct. A picture's EXIF data includes GPS coordinates, timestamp, and device information. A suspect claims they weren't at the crime scene. But a photo on their phone, geotagged to that exact location at the time of the crime, contradicts the claim. Apps track constantly. Fitness trackers log running routes. Navigation apps store search history and destinations. Social media apps record where posts and photos were created. Even when location services are off, some tracking continues. The phone pings cell towers, creating a record of approximate position. Vehicle telematics provide another layer. Modern cars log GPS coordinates, speed and direction. A hit-and-run driver denies being in the area. The vehicle's onboard system shows it was traveling on the street where the incident occurred at the time it happened. Credit card transactions timestamp and geolocate purchases. A suspect claims they were in another city, but card transactions place them near the crime scene on the day in question. The financial trail contradicts the alibi. But geolocation data has limits. GPS accuracy varies. Cell tower data provides zones, not pinpoint locations. Devices can be left behind borrowed or stolen. That's why geolocation evidence works best when corroborated. Multiple sources showing the same movement pattern, combined with other evidence. When the digital trail is thorough and the timestamps align, Geolocation Forensics creates a map. It shows where someone went, when they were there, and how long they stayed. The data doesn't forget, and it doesn't lie about location. Forensic chronology mapping. A case with dozens of witnesses, hundreds of pieces of evidence, phone records, surveillance footage, financial transactions. All of it scattered across days or weeks. The challenge isn't just finding evidence. It's organizing it into a coherent timeline. What happened first? What followed? When did each event occur? Forensic chronology mapping assembles the pieces into a sequence. The process begins with collecting timestamps. Every piece of evidence that includes a time marker is catalogued. Phone calls logged by telecom providers. Credit card transactions with timestamps. Surveillance footage with time codes. Witness statements placing events at specific times. Each one becomes a data point. Next, the points are arranged. A visual timeline is constructed, often digitally, placing each event in chronological order. Gaps appear. Periods where no activity is documented. Overlaps emerge. Multiple events occurring simultaneously. Contradictions surface. Two accounts placing the same person in different locations at the same time. As the timeline develops, patterns emerge. A suspect's movements can be tracked hour by hour. The victim's final day is reconstructed. The sequence of phone calls reveals who contacted whom and when. The map shows not just what happened, but the order in which it unfolded. A complex fraud case involves transactions across multiple accounts over several months. Chronology mapping reveals the pattern. Small transfers occur in a specific sequence, each one timed to avoid detection thresholds. The timeline shows the scheme wasn't random. It was methodical. But chronology mapping requires precision. Time zones must be standardized. Daylight saving changes accounted for. Clock inaccuracies in devices corrected. A single timestamp error can distort the entire sequence. Still, when the timeline is accurate and complete, it transforms chaos into clarity. The events don't just exist in isolation, they connect. Cause follows effect. Actions lead to consequences. The chronology becomes the narrative, and the map shows how the story unfolded. Contamination Control Protocol. Evidence collected at a crime scene is only valuable if it's uncontaminated. One mishandled sample, one ungloved hand, one uncovered sneeze, and the evidence becomes questionable. Contamination control isn't optional. It's the foundation of forensic integrity. The protocol begins before entering the scene. Investigators suit up, gloves, shoe covers, hairnets, sometimes full-body suits. The goal is to leave nothing behind and take nothing unintentionally. Every item brought into the scene is documented. Every person who enters is logged. Once inside, zones are established. High-priority areas where critical evidence is located are restricted. Access is limited. Pathways are designated to minimize disturbance. Evidence is collected using clean tools for each item. Gloves are changed between samples. Packaging is sterile and sealed immediately after collection. Cross-contamination is the constant risk. DNA from one item transfers to another if they're placed in the same bag. Fingerprints from an investigator contaminate a surface. Fibers from a responder's clothing fall onto evidence. Every precaution targets this risk. Negative controls verify integrity. Blank swabs are processed alongside evidence swabs. If the blank shows contamination, the entire batch is suspect. Chain of custody documentation tracks who handled each piece of evidence and when. Any gap or inconsistency raises questions. A DNA sample from a crime scene is analyzed, but the profile shows a mixture that includes the evidence technician's DNA. Contamination occurred during collection. The sample can't be used. The case loses critical evidence. In high-profile cases, contamination claims become defense strategies. If protocols weren't followed perfectly, the evidence is challenged. Was the scene properly secured? Were gloves changed? Was packaging sterile? Any procedural lapse undermines credibility. But when protocols are followed strictly and documented thoroughly, contamination risks drop to near zero. The evidence remains clean. The integrity holds. And when the case goes to court, the chain from collection to analysis is unbroken. The evidence is what it claims to be, untouched and uncompromised.